For the past couple of years, Bob, Meyer and myself have spent a lot of time working on a technical problem connected with a rather simple system of logic. The results of this research are, we think, both technically interesting and philosophically illuminating. So our purpose today is to try to present some of these results for your consideration. Before we start though, a few words are in order concerning the choice of presentation. Presentation of technical results in a seminar has, we think, at least two difficulties associated with it. The first of these is that even in an hour it is difficult to get to the fine details of the proof. We both recall a seminar, for example, given by Professor J.M. Dunn, in which with great satisfaction he finally got to lay out the details of the verification of the associative law for disjunction, one of the most important technical points in the proof technique of the system he was working with, the one which he had never before got to spell out in a formal seminar. The second difficulty with presentation of technical results is that the technical presentation often bears very little resemblance to the process of creation. For these two reasons, combined with the fact that the work has been a joint effort, we have decided to try a somewhat historical approach. We will try to recreate some of the conversations that we've actually had in working on this problem. Of course, we want to stress that there is no hope of an actual recreation of these conversations, and in any case we'd certainly want to leave out false starts and that kind of thing. But what we have in mind is a sort of Baudelarized version of the story, in a form suitable for philosophically mixed company. Well, are you ready, Bob?
Of course.
Okay.
Okay. I'd like to start here with our motto. Our motto is, "The revolution devours its children."
Great. Okay, now the time is, 1976. What have you been thinking about lately, Bob?
Well, Errol, to tell the truth, I've mainly been thinking about how to avoid being crushed in the poison pawn variation of the Sicilian defense. More hopefully, though, I've been trying to think about a problem of Anderson's and Belknap's. It's sort of the Fermat's last theorem of the relevant logic enterprise. Very easy to state, but very difficult to prove. Let me say a little bit about what the problem is and how it arose. Our minimal logic, a long time ago, was a concern of the 1950s. And as our elders have recounted, there was interest in those days in finding such a minimal logic. Minimality was generally explained via the deduction theorem. Everybody thought the deduction theorem should hold. And so people like Church and Moshaw-Quay, and what was later called R. Arrow, and Anderson and Belknap, and Ackermann, working on a system that was later called E. Arrow, proposed minimal logics. Given this kind of motivation, interest centered on pure implicational systems. Systems in propositional variables with an implication connective, I'll call it arrow sometimes, as the sole connective. We'll stick to such pure implicational systems. Curry argued that there was no minimal logic of this kind in a celebrated reply to Church's first papers on R. Arrow. Anderson and Belknap changed this tack, suggesting the following is a necessary condition for a minimal implication logic. If A and B are distinct formulas, A and B should not be provably equivalent. Classical logic flunks this test. Any two distinct theorems are, of course, equivalent. But so do the well-known relevant logics flunk the test, like R arrow and E arrow. For example, in R, A is equivalent to necessary A, and there are similar examples for E.
Well, I can see that that's one kind of test of minimality, but actually I think that, as Routledge has put it, a truly minimal logic in the sense of being acceptable to all comers would no doubt have no theorems whatsoever. I mean, why this particular stress on this kind of aspect of minimality? I mean, for example, I can think of your system, B sub arrow, the system you developed with Routledge, in which the only axiom, the only theorems of those are the form A arrow A. You know, since we're going to develop in the course of this seminar arguments against AROA as a theorem of logic, it seems that there's an example of a minimal system with no theorems whatsoever. But to return to the Anderson and Belknap criteria, which I guess more or less says that the algebra of formulas is to be the Lindenbaum algebra, and that's the sort of criteria of minimality. Why did Anderson and Belknap pick on the system P minus W?
Well, Anderson and Belknap approached this problem from the top down. Here are a highly redundant set of axioms for classical implicational logic. I don't know if you can see this too well, but at the very top here, there's the Peirce law. P implies that Q implies that P implies P. Followed is the principle of paradox of material implication, often called K by people in the Curry school because of its connections with combinatorial logic. P implies that Q implies P. Following is the principle of assertion, as Anderson and Belknap have called it. P implies that P implies Q implies Q. The Curry combinatorial name for that is CI. Here comes a really bad principle. P implies itself. This is the I principle on the Curry scheme. This next axiom looks a little strange. It's of the form P implies that P implies Q implies that P implies Q. However, in order to get some forms of the deduction theorem, you need this kind of axiom. It's the W principle. Finally, leaving what in fact are a bunch of questionable axioms, we get solid syllogistic principles. P implies Q implies that Q implies R implies that P implies R. That's the B prime principle. And the final principle, which may look like the B prime principle, but it's not, is Q implies R implies that P implies Q implies that P implies R. Now when Anderson and Belknap started to look for their minimal logics, they began by throwing out Peirce, and they threw out the K principle, since those were thought of as paradoxical. But in their formulation of R, following Church, they kept the CI principle, and even in E, they kept what is essentially a weaker form of it, namely this CII principle. P implies P implies Q implies Q. Moreover, they kept identity, and they kept the W principle. However, having weakened the CI principle to get E, they weakened it still further by throwing out even CII to get what they call their system T of ticket entailment. Then to get P minus W, they threw out this contraction principle W, leaving them merely with the two forms of transitivity, which I guess everybody can agree are okay.
Yeah, well, the second principle of transitivity that you've got here, this principle B, well, that's just the syllogism in Barber, isn't it, I guess?
Exactly right.
All Q's are R's implies that all P's are Q's implies all P's are R. But, okay, well, in any case, it's very different from the B prime principle, although it's kind of, normally you just think of them as the same, okay? I mean, the same principle.
Yes, they are very different, right. Though I'd like to point out that I guess you're suggesting that we might possibly do without the B prime principle and just have the B prime principle.
Something like that, yeah.
Well, if you're going to have contraposition principles anyway, you can't do that. Because if you just look at this B principle, Q implies R implies P implies Q implies P implies R. If you just contrapose all of those small entailments, you get not R implies not Q, implies not Q implies not P, implies not R implies not P, which is just the B prime principle back again. I would like to mention one thing, one more thing, that the Anderson-Belknap conjecture is just trivial if you don't have the B prime principle, and since obviously any good results in logic are going to require hard work, such as you did, surely we don't want to rest with this weak system just based on B.
Okay, well, so if you chop down these axioms right down to just a principle B or something like that, you get a very easy proof that the system doesn't collapse in any distinct formulas. But
Right.
what was the situation? We started chopping down, we got down as far as T, which I guess is just got the last three axioms plus identity. And what's the situation of the conjecture from that point of view, from the point of view of T?
A very good question, actually. A very good question, of course, partially dependent on the fact that you know the answer. In fact, the conjecture was first proposed for the system T. In fact, Belknap found a counterexample to the conjecture that T doesn't collapse any distinct well-formed formulas. And so, nothing daunted, Anderson and Belknap tried again, chopped out the W principle, which was the main thing which produced the counterexample, and proposed the conjecture for the system that, by the way, they have come to call T minus W, but it was originally called P minus W. So there's our problem, which still remains unsolved after 2 decades of graduate students and eminent logicians alike beating their heads against it.
Okay, so the situation is that when you start chopping down, at least at the T level, the conjecture is trivially soluble and fails. We know that if you chop out the B prime principle, the conjecture is also trivial and holds the system, so we're stuck on P minus W then. It's just what's been going on with P minus W then.
That's right. That's exactly the situation that we're in. Now, in fact, the dramatic requirements at this point are that Errol is not allowed to know the results of his own research at this point in the discussion. Moreover, he hasn't yet passed his PhD exam at this point, and so he rightly feels cautious about making his supervisor look too dumb.
Well, I'm not sure I understand those last remarks, but can we go back to why the conjecture is trivially true if we drop the B prime axiom?
Well, let's discuss that point in the context of the actual work that's been done on the P minus W problem. In fact, most of the work has just led absolutely nowhere, and only 3 people have made contributions that advance the problem at all. The first was Belknap, who Gensonized the system and provided it with a decision procedure. Details are entailment. The second important contribution was made by an American philosopher named Larry Powers. Parry's essential contributions were these. First, he investigated the system that one gets by dropping P implies P and sticking with the 2 transitivity axioms, getting to what's been called P minus W minus I.
Look, can't we call that just system S for simplicity or something?
S for syllogism. Very good.
Right.
Anyway, Powers came up with the following conjecture. For no formula A is A implies A theorem of S.
Well, if every theorem of P minus W of the form A arrow B, where A and B are distinct, were already provable in that system, the system S that Powers investigated, then Powers' conjecture, the one that you just stated, that for no formula A is A arrow A theorem of S, would already imply Belknap's conjecture, wouldn't it? The kind of argument I'm thinking of is as follows. Suppose that Belknap's conjecture is false. Okay, we're going to try and argue it by contraposition. Well, if Belknap's conjecture is false, then we have a pair of distinct formulas A and B, such that both A arrow B and B arrow A are theorems of P minus W. Then, of course, if you could show that in that situation any such theorem was also a theorem of the system S, we'd have that both A arrow B and B arrow A were theorems of S. But then, of course, given this transitivity principle B, since A arrow B and B arrow A are theorems of S, we'd have that A arrow A was a theorem of S, which would contradict Power's hypothesis.
Well, as a matter of fact, that's just what Powers proved. And the amazing thing is that just to work on the Belknap problem, what Powers had to do, essentially, was to reinvent Curry's combinatorial logic. Moreover, Powers' idea for the solution of the problem had a very heavy flavor of combinatorial logic to them, by one of those mysterious but illuminating coincidences on which the universe coheres with combinatorial logic as its key.
Well, all I can do is agree. Well, anyway, who was the final guy who contributed to this problem?
He was a former student of mine, actually. His name was Robin Dwyer. Dwyer applied the theory of what I called meta-evaluations to the study of P minus W. I should mention, incidentally, that Dwyer thought of them independently. Briefly, a meta-evaluation combines an ordinary classical semantic truth condition with some extra condition, generally of a syntactical kind. For example, one might define a class of evaluations on a modal logic, say S4 for specificity, so the truth functional connectives and or not are respected truth functionally, but the condition on interpreting necessity is something like necessary A is true both if necessary A is a theorem of S4 and A is true on the valuation. Anyway, it's an interesting property of S4 that it's coherent. All its theorems are true on all meta-evaluations, which has some philosophical significance. S4 respects its own criterion of necessary truth. Dwyer, in his application of the ideas, had the same idea for implication. He defined the following valuation, which I'll call V. We only have to concern ourselves with one potential variable, P, so I'll let VP be false. Okay, now make V of A arrow B true, just in case first, either A arrow B is a theorem of S, or A and B are the very same formula. And secondly, if you made A true, you have to make B true also. So this condition for statements A arrow B being true is sort of half syntactical. It's got to be a theorem of S, or A and B are identical, and moreover, the semantical part, if A is true, then B is true. Well now, let's consider this valuation. You can see pretty quickly that it makes the transitivity axioms, the VB prime axioms, true. But it also makes A arrow A true because it allows that A arrow A can be the same formula, or A and B could be the same formula. So to make a long story short, all of the theorems of P minus W come out true on this meta-evaluation. But if you have a formula of the form A arrow B, where A and B are distinct, then the syntactical part of the truth condition says that A arrow B has to be a theorem of S. So what the inductive argument in fact proves is that if A arrow B is provable in P minus W, and A arrow B and A and B are distinct, then it's already provable in S. And that's the simplest way to establish Powers' conjecture Belknap's conjecture, if you had Powers' conjecture, through that, just going through that little argument that you went through a few minutes ago.
So I guess you just step through, essentially step through this class of defined truths, defined with this double truth condition thing. There's at least one other thing you could do with a similar methods. You could try seeing what happens if you replace the rule of modus ponens in the system S, or P minus W, with just the rule forms of the axioms instead of modus ponens, and the kind of rules I'm thinking of then are prefixing rule, suffixing rule, and a rule of transitivity.
Well, what do you mean by prefixing rule?
A prefixing rule would be a rule form corresponding to the prefixing axiom, the B axiom.
Oh, something like if A implies B as a theorem, then C implies A implies C implies B as a theorem.
Right, yeah, as if you had no exponents around.
I see.
You're just applying it directly as a rule.
Okay?
The idea is that the axiom is stronger than an axiom that also licenses theorematic replacement, something like that. But you could define a similar valuation, or using similar methods to those Dwyer methods, in order to show that these systems are in fact the same, by stepping through a class of truths that you define. The kind of valuation would set, I guess, A arrow B true just in case it's a theorem of this new system with just the rules. Let's call them the Dwyer rules. And as a second part of the condition, just as you said before, that if A is true, then B is also to be true. That would be the truth condition.
Now that you mention all this, it's funny, you just jogged my memory a bit. And that was exactly Dwyer's second contribution. So let's speak about Dwyer formulations and modus ponens formulations of systems. And note that in a relational understanding of entailment, a Dwyer formulation is particularly revealing.
So these Dwyer rules are actually key to, if you like, the essentially relational nature of entailment. It seems to me that that's what entailment's like, which is what we're supposed to be investigating when we're investigating logic.
Sure is.
The relation between, well, in this case, the premises and conclusions of good arguments.
Yeah, well, that's certainly what logicians have historically thought, though if you read the journal Symbolic Logic these days, one may have the feeling that the entire area has been given over to the recursive topologists. Let us, however, be traditional in all things, as we continue the work of the relevant Red Guard in dismantling what has been called classical logic since 1910.
Okay, well, we've heard enough about the problem now, so can you tell us some more about how attempts at solutions have gone, Bob?
Well, let's return to the triviality of the conjecture for the system with just the prefixing axiom B and the identity axiom I, for start. This BI system also has a Dwyer formulation, and it again suffices by Power's Dwyer type arguments to show that no A arrow A are theorems of the system, with B axiom and prefixing rule alone. But that's clear, since what one shows in the system on inductive hypothesis is that if A provably implies B, then A is shorter than B. And that happens to work for all of the theorems of the BI system.
Oh, right. So you can carry out a little induction there. I mean, it's sort of true of the axioms, and then you just show that that property is preserved when we apply the rules.
Yeah, sorry, it's not the BI system, it's just a system that you have B as the sole axiom.
Well, I mean, that at least the base case is true in the case if we had both prefixing and suffixing in as axioms. So, I mean, that's the system S.
Yes, it is. However, in fact, one internationally famous logician, whom we shall allow anonymity to protect, tried exactly this argument for S, claiming the conjecture valid after he said, having thoroughly checked the B axiom and assuming that the B prime axiom would work just like it. But if you think about it, it really doesn't, does it? Think of some reason why the B prime axiom might produce antecedents that are longer than consequence?
Uh-oh. Yeah. Okay. Suppose we had A shorter than B. Suppose we had a theorem of the form A arrow B where A was shorter than B, and we applied the suffixing rule.
Right, yes.
So we'd obtain a theorem B arrow C implies A arrow C, but then B arrow C is going to be longer than A arrow C, and it's now in the antecedent position.
Yeah,
so it's this
right.
twist, this B prime twist has done that proof in.
Right, yeah, right. That's exactly the point. And in fact, lots of attacks on the problem have depended on some sort of measuring of lengths of formulas or something like that. At any rate, they've tried to impose a simple order, a linear order, on P minus W propositions, maybe a matrix in the natural numbers or Gödel numbers or something, where if A arrow B is provable, A gets a shorter number than B, or a smaller number than B. Now actually a little argument that I won't go through here shows that no such linear project, no such Gödel numbering project is going to work under certain very large, very general conditions. Another line on the paper, on the problem, has been matricization. People try to find matrices that would dispose of all the A arrow A. Lots of people have tried to find a finite matrix, for example, a three-valued one, in which all the A arrow A would turn out false, whereas the prefixing and suffixing axioms would turn out true. But in fact, a simple extension of an argument of Tarski's will show that this can't be done. There's no single finite matrix that could possibly reject all the A arrow A while making the transitivity axioms true. So the P minus W problem is most definitely not solvable on the cheap. But it's characteristic of the real advances, like those mentioned above, and yours for that matter, that they don't come easy. As Belknap would say, the Puritan principles, again verified, only hard work and a clean life suffice.
Well, to tell the truth, as modest a man as I am, I'm itching to get round to explaining all my hard work involved in solving this problem, but I won't talk about my clean life for the moment. But actually, getting back to your remark about matrices, it's easy to show that where for PROP, that PROP, that is that formula where P is a propositional variable, is not a P minus W theorem. So at any rate, the scheme AROA can't be an actual theorem scheme of P minus W, of S, I'm sorry.
That's right.
The problem has got to be then to show that for each instance A, AROA is not a theorem.
That's right. Now what does AROA remind you of, just logically and philosophically?
It reminds me of the fallacy of begging the question, actually.
And is that reasoning?
Well, I don't think it's any kind of reasoning at all. I mean, logic ought to express ought to characterise our idea that in reasoning we get somewhere. We move from A to B, where A and B are distinct points. We have a starting point and a destination. And AROA isn't like that at all. It gets nowhere. So I don't call it reasoning.
I certainly don't call it reasoning either.
But nevertheless, it has been a theorem scheme of so many logics. Indeed, it was called the archetypal principle of inference in a well-known recent treatise, I believe.
That in fact is true, and it's really rather crazy actually that an outright fallacy should be made the archetype of all inferences.
Well, there's another point here too, that given that AROA is a fallacy, it ought to be always false. Okay?
That's right.
I mean,
yeah, that's the main point here.
It's not
right.
like any kind of non-theorem. I mean, it's not just a contingent truth, perhaps, or something like this. I mean, it's just downright invalid whenever we use it for any choice.
Right again.
So the conjecture really expresses the correct. I mean, that's the kind of thing that we would want to establish about AROA.
And this is an important point about formal systems generally. I mean, because there are some arguments that are invalid on account of their form. Now, I mean, people dwell on the thought that arguments are logically valid on account of their form, and they tend to think of an argument as logically invalid, just in case there's some instance of the scheme which is such that you can truthify the premises and make the conclusion false. But there are some argument patterns just never any good. And repeating yourself is certainly one of them. You assume A, you conclude A. That's never a good argument, whatever A is. So the fact that PROP is invalid just doesn't help much. We really do want, as you're suggesting, all the AROA to be invalid. Actually, we can sort of think of a kind of a general scheme of this. Let's call a system lax if there are no universally invalid formulas in it whatsoever. That is, if every formula has a substitution instance which is a theorem. Now, would you believe the fact that almost every well-known implicational logic is lax? I mean, it sort of means that there are no bad arguments. They're just bad instances of good arguments, which is ridiculous. It's not confined to classical logics, by the way. I mean, it's true of R, it's true of E, and E arrow, and E arrow. Every formula, even these ones that Anderson and Belknap go on about, has a valid substitution instance, and therefore, I mean, is the argument form of something they consider a good argument.
In some sense justified by the existence of that theorem. Okay, well that it must apply to the pure implicational fragment actually, because you get these discussions of negated entailments not implying entailments, and that.
Oh yeah, sure.
So at least we're
but if we're just dealing with what's called the heart of logic, I mean,
okay.
or actually this is true though. Negation does change things a bit, but not too much actually. I mean, even in R, for example, the only universally invalid formulas are truth functional contradictions. Everything else is potentially valid, has a valid substitution instance. Well, I mean, think about A implies B implies A, for example, in the relevant logics. I mean, that's supposed to be a big fallacy, right? I mean, but as a matter of fact, I mean, they allow instances of it. I mean, A implies that A implies A, for example, the theorem of R.
Yeah.
Of course, it's a fallacy of relevance, I suppose, that if A and B are relevant to each other, that'd be okay for this to be, to have valid substitution instances, but I can't think of any reason why it would ever be okay for A arrow A to have valid substitution instances. I mean, far less all of its instances being valid. I mean here we have a horrible thing in the history of logic. I mean, the thing, absolutely none of its instances are valid, and everybody goes around asserting them all.
Well, yeah, what is this phenomenon that you've got onto here with laxness? I mean, it looks as if ordinary logical systems, as if we ought now to distinguish between two kinds of fallacies from the point of view of a logical system. From the point of view of a particular logical system, there'll be, as it were, the universally invalid ones, and then also there'll be the plain old invalid arguments.
Right.
For example, I mean, now what you're saying then with this laxness thing is that most systems only allow the plain old invalid forms, and they have no universally invalid forms of argument whatsoever.
Right, and of course, as you just said, I mean, the AROA is considered the archetypal form of inference by certain logicians, not further to be named here. And if I may be so bold as to introduce some philosophy into the discussion, that has an idealistic smell. It seems to say that A doesn't imply B unless on some transformation B can be reduced to A itself, an explicit identity.
Well, I think that one thing's clear, that no good logic should accept A or A in any instance at all.
Well, what about the traditional law of thought, that A is A?
Well, A is A. I mean, that's a law of thought, all right? And I know that most people call it the argument form A arrow A, the law of identity, which is that traditional law of thought also. But surely the thing about logic, and the thing that the Dwyer Rules have shown us, and that sort of analysis of logic, is that logic is essentially relational. I mean, the arrow of logic is not the equals of identity. And that's all.
Certainly sounds right to me, yes.
So, I mean, traditional law of thought, you can have it. I mean, I'm quite happy to have A equal to A. It just doesn't imply it. You can't infer A from A.
Yes, and if A is the same as A, that certainly, I guess, isn't any reason. That's the last reason to infer it. You already got it. Well, what do you think is the most striking feature of logical thought anyway? I mean, if you don't think this identity stuff is worth much.
The most striking feature of logic is the chain-like effect of logic, the sort of thing that you get in the syllogism in Barbara. Indeed, the sort of thing that you get in the transitivity axioms in the system that we're considering at the moment. Seems to me
really, in some sense, all of traditional logic goes back to to chains and transitivity, doesn't it? I mean, that's really what it's about.
Right. Well, there was a reduction to the first figure, and the first figure forms are chain-like forms of argument.
Right. Well, yes, the most important being, of course, Barbara, and then the E81 being the same kind of thing. Yes.
Sure.
The old principle de omni dictum de omni et nullo.
So from this point of view, the Belknap conjecture, which started out as a technical problem, now looks as if it's going to have some philosophical importance. And the question could be put, the powers conjecture, the question can be put, if you allow yourself just the chain-like rules of inference, can you get back to this fallacious law of identity, this inferential law of identity? And from this perspective that we're developing now, it seems to me that's a pretty important question. We don't want the inferential law of identity, it's just downright invalid, but we certainly do want transitivity.
Yeah, well, I have to confess that it seems to me that the usage of philosophers has certainly deproved with respect to attention to correct syllogistic reasoning from the high standards that were set by the scholastics. In fact, as late as Leibniz, they were appealed to. Leibniz used to get down in his correspondence to the 11th or 12th pro-syllogism in the course of clarifying and arguing with a correspondent. These days it's hard for them even to get down to a single valid argument. But for that matter, I mean, speaking again of relevance, it's just false that logic has lately found its formal criteria in the newfangled notion of Ackermann, Anderson, and Belknap. For as the traditional fallacy of four terms suggests, relevance is carried traditionally by the presence of a middle term. And Errol, didn't Aristotle somewhere say something about a middle term?
Gee, I think he did, you know. Well, in fact, we've just been arguing, I think, that the essential feature of reasoning is the syllogism. And indeed, I think if you look at Aristotle, you'll find that the essential feature of syllogism is the middle term.
I think you will.
Completing the syllogism, we find that the essential feature of reasoning